All right. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, April 25, 2025. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a cloudy spring evening here in my hometown of Rockport, Massachusetts. Conceived during the COVID pandemic, this series of free online Earth and Space reports is celebrating its 60th episode and fifth year anniversary. Yay! These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining biosphere, and who wonder about the greater cosmos and all that it has created throughout space and time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios community accessed cable television channel. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, myriad Earth and space scientists, educators and communicators, far-flung friends, family, and other curious folk. Thank you for your active participation and encouragements. This evening, we are most fortunate to be hosting Dr. Judith Lean of the University of Colorado. Dr. Lean is a renowned solar astronomer who came to my attention after I attended her recent plenary lecture at the annual summer meeting of the American Astronomical Society. A PhD graduate of the University of Adelaide in Australia, Dr. Lean was senior scientist for Sun-Earth System Research at the Naval Research Laboratory for many years before joining the faculty at Colorado University. Along the way, she has authored more than 150 published papers on the sun and its variability over the years, decades, and centuries. Recently, she has developed models that inform our understanding of the sun's radiative impact on Earth, including possible changes to our climate as well as our space-borne infrastructure. Judith is a member of the National Academies of Sciences, Engineering, and Mathematics, a co-awardee together with the Intergovernmental Panel on Climate Change of the Nobel Peace Prize, and most recently the winner of the American Astronomical Society's George Ellery Hale Prize. This evening, she will share her insights on solar irradiation, Earth's energy source. So let's get going. The Zoom platform is all yours, Judith.
So I do share. Yep.
Yeah, you'd share. That's right.
Okay. Did it come through? Oh, hang on, I haven't pressed share yet. There. Is that working?
Bingo.
Okay, great. Thank you everyone for coming to listen to me talk about the sun. Of course, without the sun, none of us would be here. So that's always important to remember. I'm going to talk about what was once called, and even in Wikipedia, is still called the solar constant. And it's not constant, it varies, which is why it's a really fascinating thing to talk about, because the sun establishes our environment. And I'll go through in the first part of my talk how solar radiation, which is basically the electromagnetic spectrum, establishes Earth's climate, the ozone layer above in the stratosphere, and the space environment where satellites orbit. So if the sun didn't vary, then these terrestrial parameters like climate, the ozone layer, and space environment would have an annual and semi-annual cycle because of the sun-Earth distance. But I'm going to show you that irradiance observations, irradiance being the total number of photons at one astronomical unit, observations made from satellites over the past 40 years show that it's variable at all wavelengths. So I'll show you some examples of the observations and how we can model that variability by understanding features on the sun, such as dark spots and bright faculae. And given that we can successfully model the variability in the space era, then I'm going to show you what, of course, is sort of, what's the word? Sort of a brave thing to do, which is reconstruct possible changes in the past and also in the future. So that I'm going to establish that variability of the solar irradiance. And then in the last half of my talk, Okay, I'm looking for the arrow. Here it is. And the last half of my talk, I'm going to talk about how these changes affect the Earth. Okay, so here we are. This is us in space. Um, the Earth is basically a rock in space. The sun is a hot body, 5770 K, and as such, it radiates photons with basically a Planck distribution of a black body at that temperature. The photons reach Earth. The Earth reflects these photons which warm the Earth, and it radiates its own infrared energy to space. Now, what I'm showing in this slide is the surface of the sun and the surface of the Earth. But both the sun and the Earth have atmospheres. So it's not just the surface connection of the radiation that we need to understand. As you go up in height from the sun's surface through the photosphere, the chromosphere, and into the very hot corona, which is this image here, which is 100,000 degrees, then the radiation emitted differs and is actually emitted at shorter wavelengths because the atmosphere is hotter. And this radiation also affects Earth because Earth also has an atmosphere. And if it didn't, we wouldn't be here. And you can see the temperature of the Earth's atmosphere increasing dramatically in the thermosphere. So basically what I'm going to walk through is how the sun varies at all wavelengths and how it affects the Earth at all regions of the Earth's atmosphere. Now, the sun and the Earth exist in not just a photon connection. In other words, they're not just connected by photons, but they're also connected magnetically. So this is a bigger picture just to sort of let you know that we exist in a magnetic field that is formed by the Earth's magnetic field and interacts with particles and plasma from the sun. Now, I'm only going to talk about variations in photons, and you can see here that the total solar irradiance, the energy in photons, 1362 watts per meter squared, is orders of magnitude bigger than any of the other energy inputs from the sun to the Earth. So that's sort of the focus on my talk. But this is just to give you a perspective that we live in this, increasingly broader environment. So the reason that we have an hospitable temperature at the Earth's surface of 288 K is because of a balance of incoming radiation from the sun, which occurs primarily in the sunlit hemisphere at low to mid latitudes. So that comes in, heats the Earth, and the balance, there's a balance because the Earth then is hot and it radiates back to space at infrared wavelengths. So this is the outgoing radiation. And it's the balance between the incoming sunlight and the outgoing heat that establishes basically the surface temperature of the Earth, which is, as we know, like just right for habitability. Now, I'm sure everyone here knows that the concept of the greenhouse gases, which help trap some of this outgoing infrared radiation, is a source of what is identified over the past 150 years as, quote, global warming, which means that by changing the gases in the atmosphere, you're changing the amount of outgoing heat that's absorbed. So it's always been, let's say, of interest to know not just how the greenhouse gases are changing because they're absorbing the outgoing heat, but also how the incoming energy from the sun is changing. And over the years, over the 40 years almost that I've been working on this, there have been claims that the sun is responsible for the, global warming and things like that. Well, I'm going to show that that's not the case. But on the other hand, nor can you dismiss changes in the sun as causes of variability. So the incoming sunlight establishes the radiative basis of the Earth. So this is a radiative equilibrium, but it also establishes the basic dynamical patterns of the Earth. So the incoming radiation from the sun is greater than the outgoing radiation from infrared radiation at the equator, but it's less at the poles. And so this drives, so the energy, this surplus from the equator has to get to the poles because where there's less energy, and this drives what we know as the basic circulation cells in the troposphere. In other words, in the bottom 20 kilometers of the Earth's atmosphere. For example, you probably all know about the Hadley cell, where we have motions rising, heated air flows up and then it comes down. We have a Farrell cell and we have a polar cell. So these are the basic dynamical patterns that establish things like these jets, the subtropical jets. And you've probably heard about how the polar vortex, which is the polar jet, can wiggle around and be strong or be weak and affect the temperature at lower latitudes. So I'm showing you this because the sun establishes not just the radiative balance on Earth, but also the basic dynamic patterns that occur and that affect our weather. Now, that's the surface area from all and the troposphere. So that's 0 to maybe 15 or 20 kilometers. Above that, we have the ozone layer, which exists in a region of the atmosphere called the stratosphere. And of course, without ozone, we wouldn't be here either, because the ozone protects us from ultraviolet radiation that damages biological systems. Now, the sun actually creates ozone. It dissociates the ultraviolet radiation, wavelengths less than 180 nanometers, dissociate molecular oxygen. The O2 combines with O to produce ozone. But the sun at slightly longer wavelengths also dissociates ozone. So you can see that the sun's radiation is the net cause of the final amount of ozone that we have in the atmosphere. And the ozone absorbs this radiation. And this curve here, this green curve, shows you the altitude above the Earth's surface where the sun's incoming radiation is attenuated by a factor of 1 on E. This is called the optical depth. Now, for Earth, we're only concerned about radiation longward of about 300 nanometers. But to understand the ozone layer and higher, then we need to know how all of the sun's radiation varies. So the sun then establishes, because the ozone absorbs energy from the sun and heats the atmosphere in the stratosphere, this establishes yet another pole-to-pole circulation pattern above the tropospheric circulation. So if you hear sometimes about sudden stratospheric warmings, or you hear about flows down at the poles from the stratosphere, that's because of this pattern, of this circulation pattern in the stratosphere that's also established by the sun. Now, going even higher into the thermosphere is basically the edge of space, if you like, above about 100 kilometers. The temperature of the atmosphere increases dramatically, and that's because the sun's extreme ultraviolet radiation, wavelengths less than about 100 nanometers, are absorbed by the primary gases there, which are O2, N2, and O. And this establishes yet another dynamical pattern on top of the stratosphere and the troposphere. And as well as that, embedded in the thermosphere is the ionosphere. Now, you probably know about the ionosphere because it's a layer of charged ions and molecules that exist with maximum density near the equator, because that's where the incoming solar UV radiation is. And it's a layer that reflects and refracts radio waves. So, for example, some of the original radio communications relied on the ionosphere to bounce the radio waves to a receiver. So the sun's extreme ultraviolet radiation causes the ionosphere. So you can see that the sun is like, of course, as we know, so I mean, it's not saying anything nobody knows, but it's fundamental to everything that we do on the Earth. So it was very interesting, to actually learn that the total solar irradiance, which is the energy at all wavelengths, integrated of all wavelengths, varies. So that number 1362 that I showed you coming from the sun to the earth actually varies by about 1 watt per meter squared with an 11-year cycle. Now, I'm sure everyone knows about the sun's 11-year cycle. This is something that you see in sunspot numbers, which I'm showing here on the bottom. Every 11 years, there's an increase in the number of sunspots, and the sunspots are these dark regions here. Sunspots are simply an indicator of how active the sun is. The sun is an active middle-aged star. It's driven by an internal dynamo, and that dynamo, and I'll show you how that works in a few more slides, but that produces changes in the number of dark regions called sunspots and bright regions called faculae on the sun's disk. In fact, the bright regions called the faculae and the dark regions both vary with solar activity. And you can imagine, like, this is a picture of the sun showing the bright regions. If there's a bright region on the sun's surface, then it enhances the radiation leaving the sun. If there's a dark region, then it blocks the radiation. So the total solar irradiance that we've measured from space, and that varies with an 11-year cycle, is varying because of the competing effects of the bright regions and the dark regions, and they're shown here. And in our sun, a middle-aged star, the bright regions win. So the net effect is a positive increase during the 11-year cycle. When the sun is more active, the total solar irradiance is higher. Now, for stars a lot younger than the sun, they tend to be dominated by sunspots, so they would have a different out of phase variation with solar activity. And then stars older than the sun move from being dominated by sunspots to being dominated by faculae. So we're a middle-aged star, the sun is a middle-aged star, and both the sunspots and faculae are important for understanding its variability. And you can see in this simple model here of the changes in the bright faculae on the entire disk, the changes in the sunspots, that's the green curve here. It does a beautiful job of measuring all these wiggles. So if you look at this curve, all these wiggles, it's not noise. These are literally changes in solar irradiance, the total solar irradiance. Now, the total solar irradiance is, of course, the integral of a spectrum, the spectral irradiance, the solar spectral irradiance, which, as I said earlier, is typical of a black body radiator at 5770 K, at least in the visible and infrared spectrum. The spectrum emission in the ultraviolet and extreme ultraviolet is much higher than a black body, which would be sort of dropping down here. And that's because those emissions come from the outer atmospheres, the chromosphere and the corona of the sun. And the solar cycle energy change, in other words, the change from the minimum to the maximum of an 11-year cycle, is not the same at all wavelengths. So the whole spectrum doesn't just go up and down. In fact, the most variable part is the region in the near ultraviolet and visible. And then, but the extreme ultraviolet region is also very variable. And as a percent, the energy at the shortest wavelengths are the most variable. Now, what I'm showing you here is how the corona and the chromosphere of the sun's atmosphere produce these extreme ultraviolet and ultraviolet radiations that affect the thermosphere and the ionosphere, and this radiation varies the most. So this is where we see this in the thermosphere and the ionosphere, absolute dramatic effects due to changing in solar irradiance, and I'll show you those in the second half of my talk. As we go to longer wavelengths, the visible radiation varies by 0.1%. Now, 0.1% is enough for Wikipedia to say, well, that's sort of constant. But what Wikipedia doesn't recognize is that 0.1% of the sun's energy, 1362 watts per meter squared, is still a lot of energy. So in terms of influencing the Earth, the solar irradiance is not sufficiently variable that it makes big disruptions, but it is sufficiently variable that we can detect the changes. And I'll show you that in the second half of my talk. So given that the sun's total irradiance varies, we would really like to know how it varied in the past as well as the future. Now, for maybe 100 years or more, there's been interest in associating sunspots, and this is the sunspot number here shown back in time for the last 400 years, variations in sunspot with variations of parameters on Earth. For example, changes in tree rings or in ice cores or in various forms of weather, in rainfall. And that's partly because in the 1600s, from 1640 or so to 1700, there was a period when the sun, it's called the Maunder minimum, there were literally no sunspots on on the sun's disk for years at a time. And I'm sure everyone knows here that Galileo started observing sunspots right around this period. And apparently it was so exciting for anyone in that time to observe a sunspot that they would write a paper like, oh, I saw a sunspot, which is like something that we don't do today. And because, as you can see here, we're in the period of space observations in our lifetime, sunspot numbers have been really high. Solar activity has been pretty high. And so this concept of changing long-term solar activity, like in this case, solar activity associated with winter severity in Europe, is something that Jack Eddy in 1976 published. And it's one of many anecdotal pieces of evidence about the sun's influence on the Earth. So, of course, there's been a big effort to try and understand what is the magnitude of the total solar irradiance in an episode such as the Maunder minimum. So we know that it increases by 0.1% or about 1.3 watts per meter squared during a recent solar cycle. And a number of people, see, I've plotted here going back 30 years. People have tried to estimate how much did the solar irradiance decrease in the Maunder minimum. And some of these estimates are very, very large. And if the sun's radiation really did decrease that amount, then we really would have cold temperatures on Earth. So what I'm going to show you, however, is the latest results from models that Yiming Wang and I have developed that show the number, our number is something like about just about a fraction of the solar cycle. But this is just to point out that there's a lot of interest in understanding how the sun varies over time. And part of that interest is from a really increasing collection of paleoclimate evidence that shows evidence for variations associated with cycles in the sun. So there's an 11-year cycle in the sun. I'm going to show you there's also a 100-year cycle. There are other multiple cycles. And so what I'm showing you here is a map of the temperature response, and I'll explain how this is derived in a later slide, but this is the temperature response, the surface temperature response to an increase in solar activity. So when solar activity is high, then you have warming in the continental Europe and Russian area. You can see it's not uniform. So you would think, why would that be so? Since the sun's radiation comes in, heats the surface near the equator. Well, remember I showed you the dynamical motions. What we believe happens is that the changing radiation from the sun alters these dynamical patterns. And that's why, for example, these regions of influence here correspond to some of these interfaces of the dynamical systems. But you can see things like drought in the US, warming North Atlantic, high rainfall. All of these seem to be related to the sun. So we need to know how the sun varied in the past. And we need to know, in particular, it's become quite a cottage industry in the media to wonder, are we going into a new Maunder minimum? Will the sun, in the future now be a new Maunder minimum? So in 2011, which is a solar cycle ago, basically, there was a major announcement that the sun's fading. Sunspots signal a big drop in activity, and if this is true, we're going to have more minimums coming up. And this idea persisted even till a few years ago, grand solar minimum. Well, this is not going to happen. I'm going to show you why I think that's the case. What we've been seeing, and I'll explain this in more detail, in the last 40 years is a decrease in the amplitude of the solar cycle. That's true. And we've seen that decrease in irradiance as well. What I'm showing you here are some measurements of the magnetic flux on the sun, which is the evidence or the outcome of the dynamo. When this report in 2011 was made, we were at the minima of an 11-year cycle, but we were also at the minima of a longer term, 100-year cycle. And so you can see, no, we didn't go into a Maunder minimum. In fact, we are now increasing in the current solar cycle 25. The current cycle is higher than the previous cycle. So no, we're not going into a Maunder minimum. And what's more, as the tree ring and cosmogenic isotopes in ice cores show, that clusters of Maunder minima, like Maunder minima, spore minima, in other words, these minima periods tend to happen in cycles of 2,400 years. And we just had a cluster of minima back in 1700s. So if we're not going into Maunder minima, what might we be doing? And so to understand that, this is the work that I talked about with my colleague, Yiming Wang. You can run a model that's called a flux transport model of the sun. Basically, what happens is that you deposit magnetic features on the sun, and you can see here's a magnetogram showing the different magnetic features. The reason that the dynamo, the way the dynamo works is that the sun has differential rotation. Let me show you. This is an image showing how the rotation of the sun takes the polar fields at minimum, winds them up into a toroidal field, and then eventually, so that the differential rotation winds up the magnetic fields. There's a meridional flow that transports the fields from the surface to the poles, and they return back to the equator at the bottom of the convection zone. And at the same time, of course, since magnetic fields are plus and minus polarity, then there's diffusion and cancellation. So a magnetic flux transport model takes these things into account. And when we ran the magnetic flux transport model from the Maunder minimum, this white curve is what we think, or how we estimated changes in the sun's total solar irradiance. And you can see what is captured here is the Maunder minimum, which is the period of very low activity. But then 100 years later is the Dalton minimum, which is another period of low activity, but not quite as low. And then the Gleisberg minimum, and now we're in the Maunder minimum. So the sun, for our lifetime, has been on the descending phase of the most recent Gleisberg cycle. The Gleisberg cycle itself is modulated in amplitude by another cycle. So for the future, what we think, or what we're projecting, is this gray curve here. We're expecting to see another Gleisberg cycle in the next 100 years, of which we're just starting now. Now, because of all the media that I showed you about, we're going into a Maunder minimum. The IPCC, which is the Intergovernmental Panel on Climate Change, in their last simulations, I guess it was 2 IPCCs ago, they actually forecast this green curve. And they said that the sun is going to go into a Maunder minimum. Now, you can imagine, and it's true, when they put this in their climate models, well, then this change in irradiance negated some of the increased warming due to greenhouse gases. That's probably not going to be the case, but of course, we're all going to have to live another 60 years or so to actually know if this is the case. But so this is, in summary, this is our current understanding of the sun's total solar radius, and of course the spectrum varies along with this as well, the fact that we've been observing for these 40 years on the descending phase of the Gleisberg cycle, and we're possibly just approaching a new Gleisberg cycle. So with that background, the fact that the sun's total solar radius changes, the spectrum changes, it changes during the 11-year cycle, it actually changes all day, and like as the sun rotates on its axis, and it changes on longer timescales. So now what does that mean for the Earth? So remember, I showed you the temperature profile. This is the temperature at the Earth's surface, which is determined, the equilibrium temperature is determined by the incoming visible radiation from the sun and the outgoing thermal radiation from the Earth's surface. And then going up to the stratosphere, where the ultraviolet radiation from the sun creates and destroys ozone, and then going up into the thermosphere. Now, all of these regions of the sun, of the Earth, have societal consequences. So for climate change, as I mentioned, increasing solar radius warms the planet, but CO2 increases also warm the planet. So as I said, the media in particular, but people who don't want to accept that greenhouse gases are warming the planet, say, oh, it's the sun. See, it's the sun's stupid. The jury's still out on climate change, for example. So knowing what the sun is doing, or more importantly, what the sun is not doing to the climate, is really important to establish. Now, ozone depletion, since 1980, over the last 40 years, especially from 1980 to maybe 1995, the total ozone layer decreased. And that was because, it's established now, because of increases in CFCs, which is chlorofluorocarbons. Chlorofluorocarbons are chemical species that are released in the troposphere in things like air conditioning, solvents. They're inert in the troposphere, which is great because they don't affect anything in the troposphere. But because they're inert, they drift up to the stratosphere. Once they reach the stratosphere, the sun's ultraviolet radiation destroys them, and this produces free chlorine atoms that decrease ozone, that catalytically destroy ozone. So the whole issue of ozone depletion and the ozone hole, which is a manifestation, the polar manifestation of this, has led to the phasing out of chlorofluorocarbons. And so now we're in the phase, in the period where the sun is causing ozone to change. The CFCs were causing ozone to change, but they've been restricted. So we expect the ozone to decrease, but also the sun warms the stratosphere, and that changes the ozone chemistry. And the CO2, when it drifts up to the stratosphere from the troposphere, actually cools the stratosphere because it radiates to space. So I know this is all getting layer on layer of complication, but it really is an incredibly complicated system. And this balance, or the role of the sun versus the role of anthropogenic gases is really complicated as a function of altitude. Now, when we get into the space environment in the thermosphere above 100 kilometers, the CO2 gas causes cooling for the same reason it does in the stratosphere. And that's because there's no overlying CO2 to absorb it. So it just radiates out of space and it cools the atmosphere. And of course, the solar increase causes warming. So you can see there are societal consequences and societal imperative to understand what the sun's changing radiation is doing throughout the entire Earth system. So I'm sure everyone's familiar with this famous plot here. What I'm showing you is the increase in the global surface temperature measured at the Earth. I'm actually showing you 4 different time series because for a while there was people who didn't want to believe in global warming said, well, let's say the temperature records don't agree. Well, they agree beautifully. You can see here, and you can see that as of this past year, 2024, the global surface temperature is now 1.5 degrees above the pre-industrial level. And that time series from in the last 150 years is shown here on a longer time series. You can see that not only is the increase of 1.5 degrees dramatic, but it's the sharpest increase. It's occurred more rapidly than any change in the last 1,000 years or so. And if you look at here on the at the maps, you can see that the increase in the surface temperature is not uniform. You can see there, it's like you think, wow, global surface temperature is increasing. So that means it's going to be hot everywhere. That's not true. You can see that there are some regions are warming and some regions are cooling, much as I showed you the distribution of the sun's impact on the solar activity. It has a very distinct regional pattern. And that regional pattern was different in the first part of the 20th century and in the most recent part. And in fact, historically, where we are now, in fact, there was a beautiful article in Science and also a talk, work by Bill Ruderman says that in fact, maybe when agriculture began about 10,000 years ago at the peak of the Holocene, that maybe is when global warming, anthropogenic climate change started, because otherwise, we would be probably going into a cooler period. But anyway, so this is just to give you a sense of where we are and how the Earth's surface temperature is changing. Now, what are the causes of that change? The 1.5 degrees C shown here can be modeled relatively well by this orange curve. I mean, it explains a high fraction of the variance, and it's a combination of primarily the increase in greenhouse gases, which I'm showing here as the net anthropogenic influence. And but that's 80% of it. But you can see the wiggles, all these ups and downs. That's the solar irradiance, which is responsible for about over the from min to max over the cycle, 1/10 of a degree. Now you think 1/10 of a degree centigrade isn't much, but when we're looking to attribute changes of order of 1/10 of a degree centigrade in our record, then we need to know all the natural things that are modulating the anthropogenic things. And so we have the El Nino Southern Oscillation, which is a sloshing around of temperatures. In fact, let me show you the patterns of all these things. The anthropogenic gases shown here. This is a pattern of anthropogenic influence. This is the pattern of the sun, which I showed you earlier. This is the pattern of the Pinatubo volcanic eruption. When there's a big eruption, a lot of aerosols increase into the Earth's atmosphere. So aerosols basically act as a sort of absorbing, they reflect the incoming sun's radiation. So they act as sort of like a cover, if you will, and they cool. There's the net cooling, especially at high latitude regions. Now, the El Nino Southern Oscillation, I'm sure everyone knows about that. Basically, it's a sloshing around of temperatures in the Pacific. What happens during an El Nino event, there's very warm water in the tropical Pacific. Now, we've just actually had an El Nino event, and we're now going into a La Nina phase. And that means that this hot area here in the tropical Pacific goes away and the temperatures are cooler. But the changing El Nino oscillation shown here affects the global surface temperature. So you can see we have these natural things affecting the surface temperature as well as the anthropogenic things. Now, the anthropogenic gases in the model that I showed you clearly dominate, but a misattribution of the causes of climate change has really quite significant scientific, political, social, and economic consequences, and it causes a lot of confusion. And I'm going to give you a prime example of how that happened. The Intergovernmental Panel on Climate Change, in its 2013 report, invoked what it called a global warming hiatus. It said basically that global surface temperatures in the first half of the 20th century, shown here, basically didn't warm. And they said that we're having a hiatus in global warming. And the reason was because the general circulation models, climate models that they used to make their forecast, shown here in the blue, did not predict this warming. So IPC says, well, the warming has abated. And what happened is that caused literally a decade of research reported in Nature, reported in the media, climate change, the case of the missing heat. Where is the heat hiding? You know, or every climate scientist and their graduate student came up with an explanation. Oh, the heat's hiding in the oceans. No, someone found it. It's in the Pacific Ocean. Someone said, well, the reason that we haven't had any warming for 10 years is because of China's coal burning, producing industrial aerosols. Someone else said, no, it's volcanic aerosols. Someone said, well, it's the really low solar radius. Okay. The thing is, this has serious consequences in terms of policy. So rapidly, the media basically began to say, well, you know, there's no such thing as global warming because see, the temperature hasn't been warming. And the climate scientists really received a sort of negative. They earned a negative reputation because, like, people were saying, well, you know, they don't know what's happening. You know, ask the global warming fairy. And then, of course, this then migrated to, well, if there's no global warming, then why are we spending all this money on shifting to away from greenhouse gases? So there are economic consequences. Eventually, Mother Jones pointed out that with all the explanations of the quote climate hiatus, if they were all true, then the hiatus could be explained twice over. What happened in this period from the beginning of the 20th century to maybe a decade in? We had cooling by La Nina. In other words, we did not have a significant El Nino event. And we had the sun declining in its 11-year cycle. We did not have any volcanic aerosols. So what happened in this decade? In this decade alone, the combined effect of the El Nino Southern Oscillation in a La Nina phase and the descending phase of the sun's irradiance in the 11-year cycle basically were enough to counter the increased warming over that period, over that 10-year period. And that's why the surface temperatures were flat. And in fact, there wasn't a hiatus in global warming. The warming due to anthropogenic gases kept going. Well, the issue was resolved when the surface temperature increased in about 2015. And why was this? Because of an El Nino. So the reason I'm showing you this is because it's very easy to think that, well, the sun's total irradiance, it doesn't vary by much, but why do we care? We care enormously because we need to know what it's doing in order to detect and to properly attribute the causes of the changes that we're seeing. Now, the situation in the stratosphere also caused a lot of confusion in terms of understanding what was happening on Earth. In the stratosphere, remember, I explained to you that the greenhouse gases, the CO2, they drift up to the stratosphere, and then there's no more CO2 above them, so they radiate to space. So this is the temperature, the global surface temperature at 20 kilometers, just 20 kilometers above the Earth's surface. The temperature there is declining. And so this has caused a lot of people who don't believe in global warming to say, well, of course we don't have warming because look, the satellites at 20 kilometers are showing the temperature is decreasing. It's cooling, not warming. Well, at 20 kilometers, there's a completely different mix of the El Nino Southern Oscillation, an additional oscillation called the quasi-biennial oscillation, the sun, the ultraviolet radiation, not the visible, volcanic aerosols, chlorofluorocarbons, greenhouse gases. There's a completely different mix of things affecting the Earth's atmosphere just 20 kilometers above the surface. And in fact, you can explain this temperature really well by the dominant effect of volcanic aerosols, and the warming is because they affect the chemistry that changes the ozone. And you can also see that the effective, this is basically the CFCs, the effective equivalent stratospheric chlorine, which, remember, because of the Montreal Protocol, which phased out chlorofluorocarbons, has the effect of that on ozone has actually started to recover. But the anthropogenic gases are also affecting ozone because they affect the dynamics that interfaces between the troposphere, in other words, the lower atmosphere, and the stratosphere. So we can extend this to ozone, the global total ozone. This is the decrease that I told you about due to the chlorofluorocarbons. You can see that this decrease is superimposed on decreases in ozone because of volcanic chemistry, a solar cycle now, a bigger solar cycle evident in the record than at the surface, and these different anthropogenic effects. What you can see here is that the ozone layer, even though the Montreal Protocol prohibited or decreased the use of chlorofluorocarbons, it has yet to recover. The ozone layer is not yet at the level it was in 1980 before the CFCs were reduced. But what is happening is that the greenhouse gases are changing the dynamical interactions between the troposphere, in other words, the lower atmosphere, and the upper atmosphere, for example, bringing ozone poor air up at the equator. And so the ozone is not recovering, partly because of anthropogenic effects in the troposphere. So it's a lot to absorb, but I hope that you get the sense that even just 20 kilometers above the surface, the mix of anthropogenic and natural variations is complicated in a different way, and the sun is playing a role in all of this. Now, moving higher into the thermosphere. So I talked about the stratosphere. Now I'm talking literally about 100 kilometers is basically the edge of space. Now, this is the region where the sun's extreme ultraviolet radiation varies by 50% to an order of magnitude. It causes the neutral temperature of the thermosphere to increase 500,000 degrees during the solar cycle. This is during the 11-year solar cycle. It causes the electron density in the ionosphere to change by an order of magnitude, and the total neutral density. So here's an example at 275 kilometers. The white line is the density, the total density of the thermosphere at this altitude. You can see it has a dominant 11-year cycle, and it's modeled really well by changes in the sun's extreme ultraviolet radiation, additional, in fact, influence from geomagnetic activity, which is, remember, I showed you the impact of the sun's magnetic fields on the Earth. And also at this altitude, you see a dominant and changing annual and semi-annual oscillation. At this altitude, this is the effect of cooling by CO2. So you can see it's fractional compared to the sun. It's the sun's influence on the thermosphere and ionosphere is an order of magnitude greater than the anthropogenic influence. Now, the reason why this is important is, for example, the space station orbits at in the lower thermosphere. And just to show you, this is the altitude of the Yoko satellite, which was operating from 1992 to 2000. You can see this decrease in altitude occurred because the density of the atmosphere at the Yoko orbit increased as the sun's irradiance decreased. So effectively, this satellite did not have any on-orbit propulsion. So effectively, the sun's radiation increase caused this satellite to deorbit. So as the sun's extreme ultraviolet radiation changes and goes through the 11-year cycle, then the entire density that these orbiting spacecraft travel through fluctuates all the time. And the space station, for example, has to maneuver to avoid hitting other objects. And there are, as I'm going to show you, there's an increasing number of objects now in low Earth orbit, and all of them are being affected by drag due to the atmosphere, which changes because of the sun. So that's a sort of overview sense of the whole Earth system now, and how the oh, I'm running out of time. Okay, I only have a few more slides. What I want to just briefly touch on now is the future, because we know, well, I explained to you that it's possible that the sun is going into a new Gleisberg cycle. We know that greenhouse gases are going to keep going because all the attempts to mitigate the amount of increasing anthropogenic gases have failed. And that's why we've already reached 1.5 degrees centigrade above the pre-industrial level. This was seen by the world as a limit above which the Earth's global surface temperature should not go. And that's because for every 10th of a degree beyond that, which is what we think this is a prediction of business as usual, by the middle 2045, for example, we're going to be at 2 degrees above pre-industrial. But every 10th of a degree warming above 1.5 has is more impactful on the system. So superimposed on this future temperature will be the variations due to the sun, shown here, and possibly due to ENSO, which is sort of just a mock-up. Now, in the future then, it's important to know what the sun's doing so we can know if mitigation effects, should they come into place for greenhouse gases, are actually happening. The anthropogenic forcing, the way there are a number of different pathways of greenhouse gas concentrations that were suggested by IPCC. And to mitigate this, you would have to have the greenhouse gases really dropping off a lot. So in terms of future space, currently, the North American Aerospace Defense Command tracks almost 10,000 active satellites, in 84% of which are in low Earth orbit. And there's more than 47,000 objects. So this is what space looks like. And in the near future, it's expected that many different countries are going to want to launch their own communication group of satellites. So we're in a position where sometime in the future, the number of objects in space is going to increase dramatically. And there's a thing called the Kessler syndrome, which means that as you increase the number of objects in space, especially when the atmosphere is more dense, such as in high solar activity, then there will be more collisions. And the more collisions you have, the more collisions you will get because of a runaway effect. So, in fact, the number of orbits has increased dramatically, and it increased in 2020, which, as I explained to you earlier, was the lowest period of solar activity in the space era. Now, every time there's a launch or a collision, like, for example, Chinese anti-satellite test, the number of objects, the number of debris increases. So as we get more of these low Earth orbiting satellites being launched, we're going to have a lot more satellites in orbit. And the sun we expect, is going into a Gleisberg cycle. And so it won't be decreasing. The density and the temperature in the thermosphere where the satellites orbit will be increasing. And this has shown a projection of the increase due to the sun and the decrease or the cooling due to CO2. Now, this is my final slide. What happens if we are actually able to stabilize the global surface temperature at 2 degrees centigrade warming? The only way we can do that is to reduce the greenhouse gases to 50% of what this is called a representative concentration pathway. And what that means is that this is a scenario we could be faced with in the future. The red curve is the curve due to the projected anthropogenic gases on the global surface temperature when they're reduced by a large fraction, what you can see happens is that then the natural variability becomes really dominant. So the sun's 11-year cycle, the El Nino Southern Oscillation, and volcanic aerosols are going to have much more impact on the global surface temperature. So how will we know if we do reduce greenhouse gases that the surface temperature is decreasing because of the decrease in the greenhouse gases or because of these natural effects? So that means, and that's also true, not just at the surface, but going up through the atmosphere to the ozone. If we are ever to mitigate the anthropogenic effects of humans on the Earth's atmosphere, then we have to go through a period where those gases are decreased and the natural effects due to the sun and natural oscillations becomes dominant. So that's another reason why the sun is crucially important. It's crucially important to know what it's doing and what it's not doing so we can know what the anthropogenic gases are doing. Okay, so this is my summary and some questions. I hope you're all convinced that the solar irradiance changes on all timescales. There are a lot of questions for the future. Why does the sun produce a certain amount of sunspots and a certain amount of faculae? Because it's the balance that affects the radiance. We don't know yet how the sun determines what that balance is. We know that the changing solar irradiance continually modulates the Earth's surface temperature, atmosphere, and ozone, and I hope I've convinced you of that. But when and at what temperature will the global surface temperature stabilize? Will the ozone densities ever recover to their pre-1970 level? We know that societal infrastructure depends increasingly on space. If we keep launching multiple satellites without cleaning up the debris in the Earth's thermosphere, especially as the sun's UV irradiance increases, will we actually reach this Kessler effect, which makes low Earth orbit uninhabitable for future spacecraft? I don't know the answer to that, but we need to keep monitoring the sun for the indefinite future so that we know the answers to this. So thank you. I finished.
Wow. Thank you so much, Judith.
Sorry, I do talk a bit quickly.
Oh, yeah. You're as brilliant as the sun.
If only.
So, the rest of us, please feel free to unmute and ask questions as you see fit.
Thanks, Judith, for terrifying us.
Oh, I'm sorry, but it's important to know.
Oh,
Like,
necessary.
people ignore like climate. People say, but you're a climate scientist, like, and my friends are climate scientists. Why aren't you worried? And it's like, we're really worried. It's like nobody believes this. So that's why I'm actually really interested. I'm pleased to have the opportunity to tell you about the role of the sun so that you know that the sun isn't the reason why.
Great presentation. Thank you.
Okay, you're welcome. I'm so glad that you're able to listen.
Okay, I'll ask a question while other people are thinking of their question. You noted the Maunder minimum and how it correlated with very low temperatures in the 1600s, I guess that century of the
Right.
17th
Yeah.
century.
Low temperatures in Europe, actually.
Yeah. Is there any evidence for similar climatic changes outside of Europe?
There's a variety of like, okay, the European paleoclimate data is much more, there's much more of it than in the Southern Hemisphere.
Yep.
So it's not that there's a lack of evidence, but there's a lack of evidence that we know of, but that doesn't mean that something wasn't happening there. The other thing is that the Northern Hemisphere is continental, much more continental than the Southern Hemisphere. And the land temperatures are where, a lot of the paleoclimate records come from. But where we expect to see the influences are in that like 40-degree region, north and south, which is where the Ferrel cell and the Hadley cell interchange. So there's a lot of anecdotal evidence, but there's just not that much in the southern hemisphere.
And that includes tree rings.
I'd have to go back and look at, do you want me to, I can go back and show you the, hang on. Go all the way back. This plot that I showed you with the, here. So here's the evidence. Okay, so there's reports of warming in Tasmania, which means that in the Little Ice Age, presumably if someone had a tree ring record in Tasmania, they would see cooling. There's tree rings in Chile. But I don't know about their evidence in the Morna Minima. But
Okay.
these reports here, these scientific reports, all show relationships between the particular parameter like stream flow, tree rings, with a proxy of solar activity, such as the amount of carbon-14 in tree rings or the cosmogenic isotopes in ice cores.
Okay.
But you can see there's just not a lot of paleo data there, whereas there is a lot more in the Northern Hemisphere.
Right, right. Okay, I have another question, and that has to do, well, you still have the slides. You were showing these cellular dynamics of
Like here.
troposphere, and then you showed similar circulation patterns for higher altitudes.
Mhm.
And I was surprised to see that they went pole to pole, whereas instead of going pole to equator and then to the other pole.
Right, and that's because, okay, so I'm told by climate people that if we didn't have water vapor, then this would be like heating at the equator and cooling at the poles. That would be a pattern. Now, see the cells are bigger. This is the summer hemisphere, right?
Mhm.
Now, when you get up to the when you get up to the stratosphere, the whole reason why the stratosphere is warming is because of the sun. So in the summer hemisphere, the sun heats the atmosphere because the ozone absorbs it, and the hot air rises, and then it comes down over this is a mixed layer of the ocean, and it comes down over the poles. And so it actually starts here, but then it becomes pole to pole at the higher, this is at 80 kilometers.
Yeah, that's wild.
This is meant to be a gravity wave, like, because, honestly, the whole dynamics is way beyond me. I listened to a talk the other day. I thought I'd really like to understand more about the dynamics of the stratosphere and the troposphere, and I couldn't even understand it beyond just simple things. So I'm not really the person to answer that, but there are other people who can explain it better.
Okay, we have a question from Virginia Renahan, I believe, and it refers to changes in Earth's magnetic field. You touched on it, saying that it's only a 0.1 watts per meter squared effect. Is that right? How do changes in Earth's magnetic field come into play?
Okay, the reason, so the Earth, as you know, has a magnetic field, and those magnetic field, like you can sort of see that here. It's like a dipole, and the magnetic field extends out from the Earth like this. Now, the sun has a magnetic field, and it basically perturbs the Earth's magnetic field on the solar side. What that causes is a precipitation of particles that are trapped in magnetic fields, a precipitation of particles that come especially down in the polar regions, because that's where the magnetic fields of the Earth reach down furthest to Earth. So that means particles from the sun, which are called solar energetic particles, and also cosmic rays. The Earth, the whole solar system is moving in a field of galactic cosmic rays. And the magnetic field that connects the sun and the Earth's magnetic field, also mitigate the inflow of galactic cosmic rays. Now, as I said, the energy coming in through the polar regions and also through cosmic rays, not only is it smaller, a lot smaller than the photons, but it tends to come in at high latitudes, and it tends not to have an impact on the lower atmosphere. Having said that, there is an electrical circuit that connects the surface with the ionosphere, because the ionosphere is a charged region. And there's some evidence that perhaps changing the electrical circuit, which you do by changing the magnetic fields of the Earth and changing the ionosphere, which connects to ground currents, might have some effects. And people like Brian Tinsley have actually looked at that. The reason why I haven't mentioned it in terms of an influence on the timescales of the 11-year cycle and related to global warming is that the Earth's magnetic field changes on a lot longer timescales than I'm talking about here.
And
Yeah,
in fact, is this field weakening overall?
I don't know. Sorry.
Okay.
You'd have to get a paleo geomagnetism.
Okay, we'll get one. Is there any last words you'd like to give us as far as marching orders?
Well, you're all astronomers, right? So the sun to you is a star that you can see, but it's just another star, right? So I think that's a great thing. Keep the sun as a star in your heart.
Okay.
So
Well,
thanks everyone for
I think people are wowed, and they're going to be looking at that big yellow ball in the sky with the new
don't look at
appreciation.
it.
Okay. Well, I
Okay.
think I have to call it quits.
Okay.
And I wish you well, Judith. And thank you so much for gracing us with your insights.
Oh, you're welcome, and good luck with all your new observatory. That's pretty exciting.
Yeah, yay.
Okay, bye-bye, everyone.
Bye-bye.
Thank you so much. Bye-bye.
Bye.
Bye, Bill,
So long, Art.
Bye, Bill.
Patty, Bill, Michael.